Hi everyone and welcome back to NTE. My name is Nthabiseng and on this channel I create quality revision videos as requested by you. If that's something you're interested in, then please consider subscribing. In today's video, I want to talk about functions and their inverses. So a lot of students get confused by this section, but it's really not that hard. The first thing that confuses students is the difference between a relation and a function. Right? So a relation is simply a relationship that exists between inputs and outputs. Okay? And the graph of a relation is not always necessarily a function. Okay? So what is a function? Well, a function is a special type of relation. Okay? A function is a mathematical rule that assigns to each x value only one unique y value. Okay? So now when we talk about the inverse of a function, okay, we need to have an original function that is a one-to-one function, right? So what does that mean? It means that if our original function is a one-to-one function, then the inverse is also a function. So what happens if the original function is not a one-to-one function? Do we just throw it away? No. Okay? So if your original function is not a one-to-one function, it's what's called a many-to-one function, right? And an example, we only have one example of a many-to-one function, that is our quadratic function or our parabola, okay? So when we encounter the parabola or the quadratic function, however way you want to call it, right? If we want to have an inverse, okay, that is a function, right? What we're going to do is we're going to appropriately restrict the domain of the parabola, okay? So now we call this diagram over here. If you want to know, if you're given a graph, first of all, okay, so we're going to ask ourselves, okay, using the vertical line test, right? So the vertical line test is going to tell us whether the graph is a function or not, okay? So the vertical line test answers the question, is this a function? Yes or no, okay? If it's not a function, there's nothing else you can do. However, if it is a function, right, then the horizontal line test will tell us whether we have a one-to-one function, right, or a many-to-one function, right? And one-to-one functions are our straight line and our exponential function, and many-to-one function is only our parabola, okay? Lastly, before I leave this slide is, I just want to talk about these two ovals that you guys have seen in textbooks. Okay, a lot of students have asked me, what is this? Okay, so they see on top of the one oval they have the word input, on the other one they have the word output. Okay, so let me show you how they generate these things. Okay, so this is called mapping basically. Okay, so let's use the example of a many-to-one function, our parabola. Okay, I can rewrite this using functional notation by writing f of x is equals to x squared, okay? And you'll see the benefits of writing f of x instead of y just now, okay? So in our inputs, we see that the first input that we can have is an x of 0, okay? Right. Now let's pick another input of 2, okay? And another input of minus 2. Let's say that's minus 2, this is 2. And an input of, let's say, 8. Okay, and we will have its mirror image minus 8. Okay, now if we use functional notation, we are able to say, okay, that the f of 2 is equals to 2 squared, which is equals to 4. Okay, so when x is 2, y is 4. Okay, so when x is 2, y is 4. Sorry, over here when x is 0, y is 0. Okay, now next, the f of minus 2 is equals to minus 2 squared, which is also equals to 4. Okay, so when x is minus 2, y is equals to 4. Okay, so when x is minus 2, y is equals to 4. Okay, Then this is what confuses learners. They like, but then now, doesn't this mean that we don't have a function? No, we still do have a function, right? So notice that -2 and 2 are not the same number, right? So we still have unique x values that are mapping to a unique y value, okay? So -2 is mapping to 4 and 2 is mapping to 4, okay? But because -2 and 2 are not the same thing, right, that means that this is still a function, right? Then let's look at the f of 8. Okay, this is going to be 8 squared, which is 64. Okay, so when x is 8, y is 64. Okay, so if we write in our output circle 64, we have a mapping of x is 8, y is 64. Okay, and I'm sure you can guess what's going to happen at f of -8. It's going to be -8 squared, which is still 64. Okay, so that maps to 64 as well. Right, and that's all that this is. It's simply just telling you the coordinates. Okay. So the important thing to note is that if you're looking at these mapping diagrams, right, if you want to determine simply just by looking at the mapping diagram if you have a function or not, right, go to your y value, okay, so like 64, then trace backwards. It maps to -8, but it maps to 8 as well, okay. Then if you're confused if whether is that a function or not, ask yourself, is -8 equal to 8? If the answer is no, then it's a function. Okay. Now let's move on to the linear function and its inverse. Okay. So the following notes have been taken from the Everything Maths textbook by Siavula. Unfortunately, this video is not sponsored by Siavula. However, the notes are shown with permission from Siavula themselves. Okay. So if we say we have a linear function, we are talking about a function that meets this general formula, okay, y is equal to ax plus q, right? In this question, they were asked to determine the inverse function, okay, of p of x is equals to -3x plus 1, right? And sketch the graph of p of x and p to the -1 of x on the same set of x's, right? And this is basically the notation that we use when you talk about an inverse function. Okay, so we write p to the -1 of x. Okay, that's what denotes an inverse function. Okay, now let's quickly just talk about the original function p of x. Okay, so p of x has a negative gradient of -3. It has a y-intercept at 1. Okay, now once you've done that, at least you have an idea of what's going to happen when you plot your original function on your graph. Okay, so you know that you have to have a y-intercept of 1 and you have to have a negative gradient. Okay, then what you then do is you determine the equation of the inverse of your function. Okay, our function is linear, right? So that means that it's a 1, 2, 1 function. Okay, that means that the inverse is also a function, and thus we don't have to worry about any restrictions. Okay, that's going to come up with the quadratic function. Okay, so let's focus on the linear function quickly. Okay, now to determine the equation of the inverse, right, we are always going to be given, right, functional notation. Okay, so we're given p of x is equals to -3x plus 1, right? You're going to say, let this equal y is equals to -3x plus 1. Okay, doing this just helps making the whole swapping the variables around easier, so that you know what is moving to where. Okay, so once we are at this point, okay, where we originally have a y, we're going to write x, and where we originally have an x, we're going to write y. So that will give us x is equals to -3y plus 1. Okay, adding 1 to both sides will give us x minus 1 is equals to -3y. Okay, then we can divide both sides by -3. Okay, So in this step, if you had written x minus 1 divided by minus 3 is equals to y, like that, okay, this is also correct, and you can also stop at that step, right? However, you can also carry on by taking out a common factor of minus 1/3, okay, that will give you minus 1/3 into x minus 1, okay, is equals to y, okay, and then therefore y is equals to minus x over 3 plus 1 over 3. Okay. Now because our inverse is a function, we then convert from standard form to functional form by writing p to the minus 1 of x is equals to minus x over 3 plus 1/3. Okay. Then we can go on to sketching the two graphs on the same set of x's. Okay, let's focus on the original function p of x first. Okay, we see that it has a y-intercept at 1 and it has a negative gradient. Okay, let's pull out one other point on this graph. Let's say, okay, so when x is equals to 2, we have a y value of minus 5. Okay, so over there. So this is the point 2 minus 5. Okay, right, so let's leave that one. Okay, then if you go on to the inverse graph, okay, we see that it has a y-intercept at positive 1/3, okay, and it also has a negative slope. Okay, so minus 5, 2. Okay, so what's happened? Okay, the x and y values have swapped around. Okay, and that's because the original function is reflected about the line y is equals to x. Okay, and that's the basic property of functions and their inverses, right? All functions and their inverse, right, are reflections about the line y is equals to x. Okay, so if you're given the original function, right, the quick way to sketch the graph of the inverse, right, is to just plot points from your original function, right, by swapping the x and y values around. So when we get to the quadratic function, right, we will see very soon that the inverse of a quadratic function is not a function, right? Rather, it's a relation. Okay. However, we are going to be asked to make the inverse of a quadratic function a function, and we're going to do this by restricting the domain of our original quadratic function. Okay. So the question that they were given here is to determine the inverse of q of x is equals to 7x squared. Okay. And if we look at the properties of this quadratic very quickly, we will see that it has it's smiling. Okay, so then it has a turning point at 0, 0. Then if you find the equation of its inverse, right, remember you were given functional notation. Q of x is equals to 7x squared. Okay, you're going to say let that be y is equals to 7x squared, so that you can swap your x and y around. Okay, so where you originally had a y, you're going to write x. Where you originally had an x, you're going to write y. Okay, then we're going to have x over 7 is equals to y squared, right? Taking the square root of both sides, because this is an even number, right, we're going to get plus or minus the square root of x over 7, right? Then we also have to put this restriction that x has to be greater than 0, right? Because remember, at this level of maths, okay, underneath our square root, we cannot have negative numbers, right? So we don't put negative numbers underneath our square root. So now you have the equation of your inverse, okay? And you're going to end there. You're not going to write that back into functional notation because this is not a function, okay? Now if you plot the two graphs, both the original and the inverse on the same set of x's, this is what you're going to get, okay? Right. Now you can see that if we put a vertical line through our inverse graph, we see that it cuts at two different points, and that's why we say that the inverse of a quadratic is not a function, right? So we have to deal with that, right? How do we deal with that, right? We deal with it by restricting the domain of our original function. Okay, so the first option is to say that, okay, let's only consider, right, x values which are positive. Okay, so it's going to be, if you go to your original function, you see that at the turning point, okay, it has an x value of 0. Okay, so we're going to consider x values to the right of that and to the left of that. If we consider x values to the right, okay, we're considering x greater than or equal to 0. Okay, right. So that means that we're going to be graphing all of these x values from 0 to the left, to the right, sorry. Okay, and if we graph that, that means on the original graph, we've only graphed this arm of our function, okay? And then on our inverse, we've graphed this blue section, okay? So that will lead you to this sketch, okay? So once you have this sketch, okay, now you have an inverse, which is a function, because when you drop a vertical line through the inverse, it only intersects the graph at one point only. Okay, not only are you allowed to use functional notation, so now you can label these graphs as q of x is equals to 7x squared and q of minus x is equals to the square root of x over 7. Okay, so notice here above it was just called y is equals to the square root of x over 7. Okay, now if we consider the opposite direction, okay, so if we consider from the x value of your turning point, which is 0, and you graph all the values to the left, okay, so you're graphing x less than 0, less than or equal to 0. Okay, so this is option 2. That's the second option that you can do. Okay, so that will mean that you're graphing this arm on the left hand side of the y-axis, right? And if you reflect that about the line y is equals to x, which is this line, this dotted line over here, okay, this will give you this arm in red, which is below the x-axis, right? And that will be this graph over here. So once you've made it a function, you can then use functional notation, because when you drop a vertical line through that inverse section, okay, it only intersects at one point only. Okay. Now, I want us to look at an example, okay, so that I can point out the fact that the domain of your original function becomes the range of your inverse, and the domain of your the range of your original function becomes the domain of your inverse. Okay, so over here you don't see it quite clearly because everything is 0. So I'm going to use my own example. So the example that I want us to do simply just says determine the inverse of f of x is equals to x minus 1 squared minus 1. Okay. Then we asked to sketch both the graphs on the same sets of axes and to restrict the domain of f so that the inverse is a function. Okay, so we're going to do exactly what they did above again. Okay, now notice first that our f of x is different from the one that they used. The one that they used is the parent graph of the parabola, whereas our one has been transformed. Okay, it has been moved 1 unit down and 1 unit to the right. Okay, so remember that this is in the vertex form. So this, if you write it in general form, you have f of x is equals to a x minus p squared plus q. Okay, and the turning point from this vertex form is given simply by the point pq, right? So that means that this graph is going to have the turning point, okay, at the point 1, minus 1. Okay, so it's going to be the turning point of our original graph, right? And if we find, let's say a point, let's say f of 2, okay, that will give us 2 minus 1 squared minus 1. Inside our bracket, we have 2 minus 1, which is 1. 1 squared is 1. 1 minus 1 is 0. Okay, so all this means is that we have a point 2, 0, which is going to be an x-intercept. Okay, so let's quickly sketch that. Now let's determine the equation of the inverse of f. Okay, so remember we're going to say let f of x equal y. Okay, so therefore y is equals to x minus 1 squared plus 1. Okay, then we're going to interchange x and y. Okay, so where we originally had a y, we're going to write x. Where we originally had an x, we're going to write y. Okay, now we need to solve for y. Okay, that means subtracting 1. Oh, oopsie. If I can rewrite the original equation correctly. Okay, so we have minus 1 minus 1. Okay, so then we're going to add 1 to both sides, which will give us x plus 1. Okay, is equals to y minus 1 squared. Okay, now we're going to take the square root of both sides, which will lead us to plus or minus the square root of x plus 1 is equals to y minus 1. Then adding 1 to both sides again will give us 1 plus or minus the square root of x plus 1 is equals to y. Okay, so that's going to be the equation of our inverse. Okay, and then we stop there. Okay, we're not going to convert this into functional notation, right? Because as it stands, that equation is denoting something that is not a function. Okay, so then how do you then sketch the graph of the inverse? Well, if you're going to try and sketch it from the equation, it's going to be a little bit difficult. What we're going to do is we're going to use the original function, right? And we're going to use the fact that the inverse and the original function is a reflection about the line y is equals to x. Okay, so all the original points that we see, we're just going to swap the x and y values around, and that's what we're going to plot, and that's going to give us our inverse graph. Okay, so for our turning point, the turning point was at 1 minus 1. Okay, so you are going to go to an x value of minus 1 and a y value of 1, and that's going to be your new turning point. Okay, 0 is going to remain 0, 0. Okay, and for this x-intercept, right, x-intercept is going to become a y-intercept. Okay, so this new point is minus 1, 1. That's still 0, 0, and this is now 0, 2. Okay, and now you have the sketch of your inverse function very quickly. Okay, so the one on top, okay, is always going to be y is equals to 1 plus the square root of x plus 1. Okay, and this was going to be the negative version, so y is equals to 1 minus the square root of x plus 1. Okay, right, then in order for us to make the inverse a function, okay, we are going to have two options, right? So option 1, okay, and then option 2. Okay, option 1 is to say, right, let's go to our turning point of the original function. Okay, so if I draw the line of symmetry there at x is equals to 1, okay, let's only consider all the x values, okay, greater than. So if we consider all the x values greater than 1, that means that if we go to our original function, we're going to start at 1 and we're going to draw this piece over here. Okay, right, now if you draw in the line y is equals to x, you see that this arm that we've highlighted, when you reflect it about the line y is equals to x, it will go up, okay? So that will give you this arm on your inverse function. Okay, so that the arm that I just highlighted now. So then if you draw that on the same set of x's, okay, so option number 1 is to say if, okay, such that x is greater than or equal to 1. Okay. Option number 2 is going to say, alright, let's go to the x value of the original graph at the turning point, which is x is 1. Right. And let's consider all the x values to the left of that point. Okay. So then if you graph all the x values to the left of that point, it means that you're graphing this arm that I'm highlighting right now. Okay. Now if you use your imagination, if you reflect that arm about the line y is equals to x, you'll see that it will give you this line on the inverse, which is below the x-axis. Okay. So if you graph that on the same set of x's, so this will be then the sketches of your inverse, which is a function. Okay. So option 2 is to say if such that x is less than or equal to 1. Okay. Now let's look at option number 1. Right. Let's look at f of x, this f. Right. Now we can call this f minus. Right. That's f minus. And this is b. Okay. So let's look at f of x and compare it to f to the minus 1 of x. Right. Let's look at the domain. Let's look at the range. Okay. So if you look at f, okay, so f is the black line. Okay. Its domain is exactly this. Okay, so it's all x values greater than or equal to 1. Okay. Its range, okay, so its y is greater than or equal to minus 1. Okay. Now let's look at the inverse. Okay, its domain is all x values, right, from x is equals to minus 1. Remember, this is going to be x is equals to minus 1, right, all the way to the right. So it has a domain of x greater than or equal to minus 1. Okay. However, it has a range, right? So the possible y values that it's covering, right, is all the y values from 1. Okay, so remember this is at a y value of 1. So this point there is a y value of 1. Okay, the things I'm drawing are not asymptotes. I'm just trying to make you concentrate on the points. Okay, so it's all the y values of 1. Okay, and then it grows. Right, it grows and it grows and it grows. So it's all the y values from 1 upwards. Okay, so y is greater than or equal to 1. Okay, now notice what has happened. Okay, the domain of your original function f has become the range of your inverse function, and the range of your original function f has become the domain of your inverse. Okay, so that's what I wanted us to, the last thing that I wanted us to note about what happens between the inverse and the function. Right, so their domain and range also get swapped around, and I didn't want to use the example from the sea of ruler because it was just zeros, and zeros tend to not make people see the relationship quite clearly. Right, and if you do the same thing for option number 2, you'll see that the domain and range are also swapped around. So for those of you who are still with me, right, let's quickly summarize. Okay. If we have a function, right, that function can either be a one-to-one function or it can be a many-to-one function. A one-to-one function is our linear function in our exponential function. Okay. A many-to-one function is our quadratic function like we just saw now. If you have a one-to-one function, its inverse is a function. Okay. If you have a many-to-one function, or in other words, if we just take all these technical terms away, if we just say if you have a quadratic, right, its inverse is not a function, right? And we can make the inverse a function by restricting the domain of the original parabola, and then the inverse will be a function, right? So now let's just wrap this video up by looking at the last function, the exponential function. Okay. Now, a lot of people like to say that exponents and logarithmic functions are inverses to each other and they stop there, right? What I want you to know is that exponential and logarithmic functions of the same base, okay, are inverses. Okay, so don't just say the exponent is the inverse of a logarithmic and a logarithmic is an inverse of an exponential function. It's only valid when the bases are the same. Okay, so if I give you the exponential function, right, 3 to the x, right, and I give you the logarithmic function log x, right, are you going to say that these two are inverses of each other? No. Okay, they are not inverses of each other, right? Because this is to the base 10, right? So remember, the log is always to the base 10. It's just that it's so common. It's like the 2 on the square root, right? It's so common and understood in maths that we don't write it. Okay, so the base of a log, if you didn't know, is 10, right? So 3 to the exponent x and log x, those two are not inverses, right? However, 3 to the exponent x and log base 3 of x, those two are inverses. Okay, and 10 to the exponent x and log base 10 of x, those two are inverses. Okay, now let's look at the question that was given in the C of Euler textbook. Okay, again, the instructions are the same on the same sets of x's. Draw the graph of f of x is equals to 10 to the exponent x and its inverse f to the minus 1 of x is equals to log x, right? And those two are inverses because the bases are the same. Okay, now the exponential graph, let's just draw it, right? With a critical point over there at 0, 1. Okay, so this is the graph of f, right? And we see there, they note that the shape is an increasing graph. It is an intercept at 0, 1. It has a horizontal asymptote of y is equals to 0. The domain is all x values, and the range is all y values above the y value of 0. Okay, because it's only above the x-axis, so it's from 0 upwards. Okay, so for y greater than 0, okay, that's the range. Okay, now before I go on, let's determine the equation of the inverse. Okay, so the equation is given to you over there, right? But how would we go about it? Okay, so we would say we're given f of x is equals to 10 of x, right? Then we would say let f of x equal y, right? So therefore y is equals to 10 to the exponent x, right? Then we interchange x and y, or swap x and y around, if you want to think about it like that. Where we originally had a y, we write x. Where we originally had an x, we write y. Okay, this is the inverse function actually, but it's in exponential form. Okay, and this form is quite nice if you want to create a table of data x and y. Okay, so you would give yourself y values, okay, 0, 2, 1, and you would determine the x values. Okay, so it's a little bit different to how we usually use a data table, but if you want to see how that works, you can go look at my video on logarithms, right? So Once you have the exponential form, you then change to log form in order to make y the subject of the formula. We'll have that y is equals to log base 10 of x. Okay. And remember, we don't write the base 10, so we can just write this as y is equals to log of x. Okay. So that's how they determined that equation. Right. Then, if you draw these two graphs on the same set of axes, you'll see that there's our increasing exponential graph, and if you reflect it right about the line y is equals to x, it will give you the logarithmic graph. Okay, and these two are both parent graphs, so the point 0,1 becomes a point 1,0. So then if we look at the properties of this inverse graph, the logarithmic function, we see that it's also increasing, right? It now has a vertical asymptote of y is equals to 0, right? Its domain is now the range of, remember the range of f was y is greater than 0, right? Its domain is now x is greater than 0, right? Remember that the domain of f was x is an element of real numbers, right? Its range is now x is an element of real numbers. Okay, you can see that on the sketch as well, right? This graph is only dealing with positive x values, right? That's because the y-axis, right, is an asymptote for it, so it will never exist on the left hand side of the y-axis. Okay. They say here, notice that the inverse, right, is the function f to the minus 1 is equals to log x, and this is a one-to-one function as well, since every input value is associated with only one output value. Okay, and we can see that on the graph. If you map any of these x values, you see that all of them map to their own unique y value. Okay, so none of them have a y value that they share. Okay. And that's it for today's video, matriculants. I hope that made functions and their inverses much clearer. Until next time.